Welcome everyone to this FP Complete webinar. Today we're going to be talking about WebAssembly in Rust. My name is Michael Snoyman. I'm going to be reviewing the chat, answering questions over there, perhaps answering some questions via voice as well. But the presentation today is going to be by Aniket Deshpande. Aniket, please take it away.
Thanks, Michael. So today we are going to talk about programming for WebAssembly in Rust. So the topics we're going to cover are what WebAssembly is and how can I use Rust to program for it. Let's start with the WebAssembly part. So what is it really? It's supposed to be a simple machine model and an executable format. So it's supposed to be a stacked machine model. And there are two executable formats available. One is the binary-like executable, and the other one is a text-based. So we have a very primitive execution environment in the browser. And it is completely isolated from the browser's API. Further, it has no shared memory whatsoever with the JavaScript environment. Now, are we going to be able to do anything with it at all? And it does not seem very enticing enough for anyone to do anything with it. So we are just going to ignore all of this. Instead, we're going to rewrite something in Rust. So we're going to do something of a game. It's called tic-tac-toe. We'll soon see how it works. This is just a slide that gives us examples of what we are hoping for. It is not executable code, so it's not important to remember any of it. So as they say, when in Rust, be a typer. So we want to be able to use native types available in Rust for our business, like enums, structs, typedefs, IMPLs. For example, we have the mark, which can have either O or an X. We have a cell that can either be a nil, having no mark, or a mark. We have a grid, for example, having a vector of cells, and that keeps track of the next mark. And then we have a grid ref to do things the Rust way. We also want to be able to program like it is JavaScript, but in Rust, because that's the present state of ergonomics available in the web application space. And we don't want to settle for less. For example, we want to be able to use something like document.createElement. We also would like query selectors. We would like to add event listeners to these elements. And we would also want to have the APIs like local storage. So let's actually go and see if we can do something of this sort. I'm going to demonstrate a code that a program that I've written, but which is already. We're not going to look into the code yet. We're going to travel through, take a journey through several tools before we go to the code. I want to first demonstrate what this is capable of. So we start this game, and we go to 8,000. We have the tic-tac-toe game. How this game works is we have two types of marks, X and O, and these keep alternating. And whenever someone does a straight line, that person wins. Let's do that once more. X1. So going back to the actual thing, we want to, even though we saw that the browser's API is completely isolated from the WebAssembly machine, and it shares no memory with the JavaScript environment. Somehow, the Cargo web tooling manages to have a WebAssembly execution interact with the DOM. And we will be exploring how that works from here on. But what's more about WebAssembly itself is what we'll look in the next slide. So there ought to be some goodness to it. Otherwise, such an effort wouldn't have gone through. It is portable. It can run on the 4 major browsers on any machine. It is compact, and it can execute at near native speeds. That looks like a really good thing for performance. What else? We have a comparison of the execution cycle between WebAssembly and JavaScript with just-in-time compilation. In WebAssembly, we have the decode, compile and optimize, and then straight execute. Whereas in JavaScript, with the just-in-time compilation, we have to parse. Then there's a compile plus optimize phase that goes on. Then there is some more optimization. This is a second phase that happens after specialization of the polymorphic usage of functions. And then you have the execute cycle, and then you have the garbage collection. What else do we have because of the binary representation? You get complete control over the indirection. Indirection is a term, the most basic usage would be a pointer. It is the most basic mechanism with which abstraction is implemented all over software. The second is monomorphization, which is another term for specialization. And third is the memory layout. Now, about the memory layout, certain memory, currently, memory needs to be explicitly allocated linearly in JavaScript and in the form of an array buffer to run the WebAssembly machine on. And there is no shared memory between JavaScript and WebAssembly, as said before, but you can export and import values. And those values can only be of the numerical type. So, well, does this mean that we can only pass integers and floating points and perhaps pointers in and out of WebAssembly? Actually, it does indeed. And although we have to work with what we have. And what about other formats? So we have the binary format, which actually executes on the web browser, and a textual format, which is just a specification. Now we're going to take a very brief look at 3 ways in which we can generate the .wasm files from code. First, let's look at the most basic, which is the textual representation listed over here, in order to understand how the interoperation would work. So this is WebAssembly text, or .wat for short. This is defining the computation of the addition of 2 numbers. Now, we know that WebAssembly is a stack machine. So the thing about stack machines is that all arithmetic and logical operations do not take any arguments. Like traditional x86 register-based architectures take when they have register names as arguments to the operations. Instead, a stack machine, these operations implicitly operate on the stack. Now let's look at the code in detail. First, we start with the module definition, and it ends with the export block. We have a function, and this is actually a label, which is like a pointer. And this is the label with which this particular function will be exported. The function definition itself has the pointer, and it defines a parameter list. There are 2 parameters, each of type integer, which is 32 bits long, and then it gives out a result, which is also of the same type. On line 3, we have get local 0, which is an instruction to place the first argument onto the stack. Now, this is not an arithmetic or logical operation. That is why it takes an argument. The second one takes the second argument and puts it onto the stack. And parameter lists are 0 indexed. So you have 0 and 1. And the 5th line, you can see that this is an operation called add, which will take the top 2 values on the stack and add them. And it will push the result of this operation back onto the stack. One thing to notice over here is that I32 is a specialized instruction for integers of 32 bits length. So now let's see how this would actually work in a real browser. we go to the code first. Okay, this is not going to be an add function that we will see, but a slightly more involved example, because there's one case over here that I want to really point out. First, we'll look at the Haskell part, because both of these are slightly similar. In Haskell, if you want to get a factorial of a number, you have the first case where if the number is less than 1, you have 1. And then you have a case for n, where n is multiplied by the factorial of n minus 1. This code is also very similar. You can see that this part, which pushes 0 and then a constant of 1 and then checks whether it is less than, is similar to this. Then we have an if block. Over here, we will check that the top of the stack is either true or false. How this works is, the first parameter, the only parameter that you have for this function, is pushed onto the stack. Then a 1 is pushed onto the stack. And then the less than function or operation is called on it. This operation will take both of these values from the stack, operate on them, and push the result back onto the stack, which this if statement or if operation will check. If it is true, it is going to enter this branch, otherwise here. But one thing to note over here is that the if block also has a return type, which is similar to Haskell again. Now, if we'll go to the second case now. In the else block, you have a 0, which means that the argument is going to be pushed onto the stack. Then the argument is going to be pushed again on the stack so that we can subtract it by 1, which is this operation. Then you have a call to the factorial, which is again this operation. And lastly, when this entire stack of functions folds, you have n into, which is the multiplication. So suppose we started with the argument of 5, we would have 5 and 4 and 3, 2 and 1, and then the multiplication would happen in the opposite direction. 1 into 2, and the result of that into 3, result of that. At the end, though, the multiplication of the last number would leave the last result onto the stack, and that would be the return type. Let's look at this on a real browser. I'm going to delete this part. We're going to go over to the JavaScript file and see what that is. So we know that we are exporting just one function from the W80 file. And we're not using anything from JavaScript in there. So you can see over here is, there is a main.wasm, which is a fetched promise that is passed to this WebAssembly module or object. And there is something called exports over here. We'll look at it later. This is used for when you want to export something from JavaScript that you want to use in your WebAssembly. And this call gives us a promised object that will have the exports that we'll use, which are from WebAssembly itself. Now, this is a W80 file. It's not a WASM file. But this is the tool we are going to use to convert this file to a .wasm. Let's do that. So we have main.what and we want main.wasm. Let's also take a look at what happened there. It's a binary file. And you can see that there is a FAC over here. Cool, but that's all we can inspect. Let's head over to the browser and check what we can do. I'm going to have to open the console over here. And a static server is already running. I'm just going to load that file. And surely we have it. You can see that the JavaScript is calling the wasm module, and we have a range of 15 factorials up to the range of 15. In the network tab, you can see that there is this WASM file that we loaded. And you can also debug this file in the debugger. And asks us to refresh. You can see that this is slightly different because the JavaScript, the Firefox's debugger is adding or parsing the binary file and creating this for us. You can see that there is a type definition here and that there are actual pointers for the function instead. All right, so going back to what we learn out of this. So in this example, we did not have to allocate any memory explicitly because we did not make use of any local memory. We just use a stack. Another thing to point out would be to consider that in order to use WebAssembly in a meaningful way for our various purposes, there is going to have to be code on both sides of the situation, the JavaScript part as well. And also that it needs to be in correspondence with the WebAssembly parts that we will use. So there needs to be a sort of knowledge share between these two worlds. This seems very cumbersome because it is almost like repeating yourself on both sides. At least those parts that reference objects that are external on each side. So this is where the Rust tooling comes in. And we will now look at the most basic one available. It's WASM Mindjet. This tool is actually a combination of two tools. One is a compiler component and the other is a command line tool. The compiler component emits .wasm files directly, but with annotations embedded. And we're going to see why. It uses a procedural macro to generate the entry point for exposing Rust functions to JavaScript. In other words, this macro will generate the appropriate code in Rust to translate from your type signature to the one that JavaScript can interface with, as well as tag other information that is useful for the command line tool to work with. As of now, you can attach it to free functions, structs, IMPL blocks for those structs, and external C blocks. But some Rust features like generics or lifetime parameters aren't yet supported by this macro. But this macro or this particular component of the entire toolchain does not produce any JavaScript. For that, we have the command line tool. It's called WASM Mindjet CLI. Now, this one emits a WASM stripped of the extra info, and it will produce a JavaScript file that wraps the instantiating of the WebAssembly and other wrappers for classes and functions. In other words, this tool opens up the WASM module that Rust C generated, finds an enclosed description of what was passed to the WASM bindgen attribute. Now it has everything it needs in order to know what to generate in the JavaScript file that we will import and use. Now let's see how to use these tools in a reality scenario. We will go out of here, and if you go back to this, I have actually gone and seen, I'm sorry about it. I've gone and put together the installation of the toolchain, which is like this. And then we have the WASM bindgen CLI, which we'll use later. So we're going to go back and go to this really boring thing, and we're going to see how it works. So to start with, we'll go to the cargo.toml file. You can see that we have a crate of type C dynamic library, and then we have just a dependency called boson binding. And then in the actual source, we have boson binding as an import, and we use the macro for an external C block. This alert function is what we intend to import from the JavaScript side. And this pub denotes that we want to export the greet function over to the JavaScript side. And this greet function uses the alert that we just imported from JavaScript. Now, how do we build this? We're going to use cargo nightly build and this target. Now, what this target is that boson32 is the architecture, and unknown usually specify the something similar to Apple and Darwin or something like that. So the whole thing specifies an architecture. To generate the interop shims for JavaScript, we're going to use boson binding like this, and we're going to see what it produces. So we go over to the command line, go into Mindjet, we check cargo plus nightly build, and we'll go and inspect what this thing has built for us. Let's check target, boson unknown, debug. Okay, as you can see, there are certain things that we can actually make sense of. There is a wbind over here, which we did not see in the what to boson example. This is also a .boson file, but it has more stuff in it. It has a placeholder, it has describe. Then the other thing of notice is the boson binding throw. You can see the memory. You can see a heap base. These are just strings, but I'm just saying that we can still see that there is extra information over here. There is also malloc and free. And somewhere over here, we can see greet. There you have it. Boson binding describe greet. This is the information that the boson binding CLI tool will use, as we'll see immediately. We go to boson binding. We go to the path and say, output some stuff in this directory. And over here, surely, we will refresh and see that these are the 4 files that it generated. Let's first go into the boson file and see that the extra information has been stripped. There is, now you can only find throw over here, malloc and free, and there's no describe greet anymore. Let's also go to these TS files. These TS files are just TypeScript files. They are basically exporting types. But the JavaScript file is of very important significance. You can see that this will load up the mindjet.bg module, which is this boson file, and it will use that all throughout. You can see there's a text decoder. And as you must have noticed in the source file, we can see that we have a string literal being passed across these functions. That means the whole law of only having numerical types going across the boundary no longer applies. And that magic is happening over here. This is what the boson binding tool does. It encodes and decodes all the information in numeric types. So you can see that there is a cached unsigned int memory 8, which starts to get initialized over here. Then you have a generic get string from boson, which decodes the encoded information as a string. You also have the alert function that JavaScript is supposed to export to boson. So it says get string from boson, and then this alert is just the native JavaScript alert. You also have the other way around. You have passed string to boson, which takes an argument, which takes the argument and then just encodes it and passes it around. We have the greet function. You can see that this is pass string to wasm. Then we have return wasm.greet with that particular thing executing. And then you have the freedom of the memory. So this is how this whole thing would work. Now, in this example, we're going to run this on the browser. But before that, we'll look at the JavaScript file. So the JavaScript file that we want to use our functionality in is the one that calls greet. It just imports mindjet.js, which is responsible for loading the wasm module, and then it'll just call world on it. Let's look at this world, and then let's look at librs. So you have hello, and the world should come here, and this should be an alert as soon as we load this file in the browser. Out of respect for the JavaScript community and the things that are usually done this way, we're going to have Webpack running this. And you can see that there is an HTML Webpack plugin I'm using, so I don't have to specify an HTML file, an index.html file. So let's see how that works. Port 8080. And you have an alert. The usual thing with debugging can be done, but this is slightly more cryptic than the other. All right, going back to our case. I just want to reiterate this point I'm trying to make over here, that there are two worlds to deal with, and that communication between them is cumbersome and not clearly abstracted out yet. And this fact also affects testing. A note about testing would be, it needs to be considered in two parts. For all the Rust code, we can use the normal testing tool that Rust provides. But for the parts that use Mindjet, all of those have to actually run on a web browser, because a web browser is the only place you have a wasm machine available. So this there is another macro that wasm Mindjet as a library provides, which is called wasm Mindjet test, and it can run on headless browsers as well. Now we saw that we just imported alert, but what about not using external C blocks every time? So for that, actually there are crates called JSSys, which gives which bundles up all the external C blocks of the JavaScript API into a crate called JSSys, and then there is WebSys for the web API. Further, there's a tool called wasm pack, which combines both of these tools. So there is this whole wasm Mindjet thing becomes more ergonomic slightly with the wasm pack tool. But this is still quite cumbersome. So I'm saying this over and over again because today in the web application space, we have tools for JavaScript where one would not have to write a single line of HTML or CSS. And there is a more ergonomic way of using Rust for WebAssembly, where we can pass JavaScript, CSS, HTML, literals, etc., and much more across the boundary. That one is standard web. It is a library. It intends to be the standard library for WebAssembly in Rust. This setup also has two parts though. But these parts are more ergonomic than wasm Mindjet. First, we have a cargo subcommand called cargo web. And second, we have a library itself. This library is largely hassle-free. It actually runs on its own event loop within the WebAssembly machine. The tic-tac-toe game that we played is written using this tooling. So let's take a dive at the actual code now and see how that works. First, we would go straight to the cargo file. Over here, you have just this one particular import that is of importance. We are using Serde to serialize and deserialize JSON. As you can notice, there is no JavaScript file whatsoever in this. And this is main. We'll start here. So once you import standard web, in order to do anything with it, you need to first call an initialize function on it. It will do its initialization of whatever it needs to. I don't know because I'm not gone into the code yet. But here, next, we make a grid ref, and this is exactly like how we would want to do it. Completely in Rust, as if we have JavaScript, the JavaScript API available. So you have window local storage dot get state wrap or else make a new grid. We have an update DOM function. Over here, we take the query selector and we take one element out of the DOM and add an event listener so that we can reset the game. And then we start the standard web event loop. Let's go over to update DOM. So in a DOM, we are not going to do any DOM diffing. We're just going to have simple repaint of the entire DOM. We take the grid from the DOM itself. We discard all the children that it has as selves. We make a completely new array or list of children under it. Then we check if someone won the game, and then we save the grid. Let's first go to save grid. Over here, you can see that this is just something that inserts state into local storage. And make cell is the place where we're going to generate cells. So we document.create element of type list. We have the CSS class cell added to it. Then we set its inner contents to whatever is the value of the index on the grid. And we add an event listener to it. This time, we want to basically add whatever is being tracked as next into the index, the memory location of the index in the grid, and then we want to toggle the next chance that the player has. Then we want to update the DOM. This happens in the event listener. So now let's go to the types that are familiar to us already. There is a mark that is either 0 or X or O or X. We have to implement display for it. Then we have a cell, which is either a nil or a mark. And then a grid with the next that tracks the next mark. We implement new for grid. And then we have the type grid ref. All of these are quite familiar because this is what we saw earlier in the slide. And this is how it works. So we're going to go over to the static section and see the index file. You can see something very fishy over here. This is the Rust wasm webinar.js file, but we don't see any JS over here. All we have to do is include one particular JS file, which is the same name as the project, for use with this cargo web and standard web tool. We're going to see the target. And if you see, this build will generate some path information. It's going to generate the JavaScript file for us, which does a lot of magic, as you can clearly see. This is much more complex than the wasm bindgen tool had for us. You can see that this is quite complex. And it can pass even, it has macros to pass JavaScript string literals, CSS string literals, and HTML directly across the boundary of JavaScript and WebAssembly. And this is the coolest thing we found so far. And this is the WASM file. It has a bunch of metadata that it needs. Now, coming to the final point of what we wanted to discuss. Well, we will go to the questions, but first, the final point that we wanted to make was that historically, we had the performance problem and the manageability problem as web applications started to become more and more complex. At the time when JavaScript was actually invented, it served its purpose, it served its imagined purpose. But because of the ubiquity of this particular environment, we, as software developers, stretched it very far. And today, it's a platform in its own state. So the original interpreter had a parse, evaluate, and execute, and then garbage collect phase. So this was just an interpreter, and it was having no way of optimizing the execution, because it would just evaluate the code as a programmer would have written it. Then there was JIT, the just-in-time compiler. It had a parse, compile, optimize, specialize, and optimize, execute, and collect garbage phase. And then we have WASM today, which is just decoding, compiling, and execute at near native speeds. This is really cool. The other side of manageability, for JavaScript as a language, we all know that there have been several attempts to contain, I would say, the problems of JavaScript when it comes to scaling software development. jQuery was the first sensation. Today we have React, things like React and Vue, and several others, which take the pain away a little. There are alternate languages like CoffeeScript, ClojureScript. There have been ECMA proposals for ES6, ES7. Type systems came into the picture recently, like Flow, and then you have TypeScript. There are several other languages that want to be able to have similar syntax as their own, yet transpile to JavaScript. Some of them are really good with the type systems, like PureScript. Yet all of them had to target JavaScript. So now is the only time that WebAssembly is making it easier, or let's say more direct, for any kind of language to actually target the web as if it were a native platform. That's the end of the presentation. I hope I was clear enough, and I hope I have done justice to the subject. Do you have any questions?
Firstly, thank you very much, Aniket. I'll monitor for questions coming in from the text chat or from Q&A, and I can pass them along. One thing that some people were curious about earlier was your usage of SpaceMax. Yeah, so if you want to just tell some people a little bit about your setup. People seem to be very interested in the presenter's editor setups. So if you want to share a little bit about that while people come up with some questions.
Cool. So, all right. So SpaceMax, I'm going to just first show you how this works as against a traditional Emacs setup. So in traditional Emacs, you have something called a meta-X. This is also available in SpaceMax, in the sense that this is just Emacs, but it has this bunch of, I would say, layers, which the community of SpaceMax has put together, and they intend SpaceMax to be used as you would use Vim. I come from a Vim background, and I recently switched to SpaceMax because it's really very cool compared to the Vim environment. Recently, there was another project that was released called SpaceVim. Now, imagine this. There's Emacs and there's Vim, and there's war between these two. And then SpaceMax makes this project where it's going to use Emacs to code like Vim and extend the modal editing philosophy of Vim to such an extent that literally everything under SpaceMax is modal. including the commands. I don't have to go to meta X. I have to just press space. If I press space, I'm going to get all of these options that I can go through. So for example, if I want to zoom the text, what I'm going to do is I'm going to press space, press Z, and you can see that there's an X that leads to scale font transient state. I press X, it leads me to this. Over here, all I have to do is press plus. You can see the text growing, or minus, or 0. So this is the modes. In the sense, I press space, this gets me into the command mode. I press Z, which gets me further deep into the tree, and then I press X. So basically, suppose you want to do anything at all with this editor, all you have to do is type single characters on the keyboard as if you were typing, and it would lead you to that command. There is one very cool thing called Maggot, which is actually an Emacs thing. So I do this, and what I did just now was space. Then you can see that G gives you Git and version control. So you press G and you press S for status, Maggot status. So it's so fast that if I want to go to, so I'm here in the file explorer. I just press space GS and I go to the Git directly. It's so fast. Now, coming back to the war of the words. SpaceMax, the community embraced Vim as a philosophy and turned Vim's modal editing to a whole another level. Now, Space Vim is a project that intends to just copy all of that and bring it back to the Vim environment. So, is there anything? Yeah, I would also like to show you my setup. So, this is the configuration file of SpaceMax. It has something called layers. So in a traditional Emacs setup, someone would have to actually write functions that work for them in Emacs Lisp, something akin to this. I have commented out all of this code simply because all of this functionality gets taken care of by simply adding a layer now. I'll show you the layers that I'm using. But before that, I'll also show you my setup for web. So this is how you would have to program. This is Emacs Lisp. Lisp is, I would consider Lisp much more, better to look at than Vim script, where you write plugins in Vim. And as for the layers, all you have to do is just add a layer, and you would have all the functionality with it. For example, I showed you that Git works just out of the box, and I can show you that Git is just part of one line in my configuration. And if I want to see anything at all, let's say I want to have commands that let's say I want to show you commands that only Git has. For that, I would have to press M, which gives me into the meta or the subtree of the buffer that I'm using. So this is the state of the buffer, and it has a major state and minor states. So you can see that if I press M, it knows that if I press another M, it knows that I want to merge. So if I press another M, it will just go ahead and merge it the usual way. The other one is log. I pressed L, and it brought me the switches that I can use on git log directly. So log current, log, stuff like that. I hope I have shown you enough of SpaceMax.
Awesome. Thank you, Aniket. We do have a few questions on WebAssembly that I wanted to raise. So here's a pair of questions that came in together or are similar enough. How do you distribute your WASM implementations? And so WASM distribution ends up being much the same as distribution for traditional JavaScript lib.
Yes. Absolutely. Yes.
Yeah. So I can also speak to this a bit. When I've gone ahead and distributed, it's toy applications in my case, but when I've distributed these things, it's basically just uploading the WASM file in the same way that I would upload a JavaScript file or anything else, any other kind of static resource. So it's pretty straightforward. Okay. Have you used this on bigger things than tic-tac-toe? Also, do you use WASM in production already?
All right. I can answer that question, but I will have to use anecdotal references. I myself have not used this in production, although I know of one particular case which has. So there is this company called Unity 3D. They make a game engine, and it seems that they have a cross-platform what do you call it, offering for their game engine. One of the targets they have is WebGL. And as of a few years ago, I think that was last year, they ported their entire WebGL target from ASM.js, which happens to be a very small subset of JavaScript, which is very happily optimizable by the just-in-time compiler. They ported their entire code base to WebAssembly on, but using C++. And I quote directly that they said, WASM is faster, smaller, and more memory efficient than ASM.js, which are all pain points of the Unity WebGL export. WASM may not solve all the existing problems, but it certainly improves the platform in all areas. Nevertheless, please be mindful that performance can vary depending on the browser implementation. The good news is that all vendors are committed to supporting and improving it. Unquote. So it looks like WebAssembly is a very good thing when it would add significantly to your performance feather, I would say, when you want to port computationally intensive tasks to WebAssembly. But the other way around, when you want to do a web application, let's say, that uses a lot of JavaScript and WebAssembly interoperation, I think that is not going to be so performant as native JavaScript.
Just to throw in one other use case that seems very strong for Rust and WebAssembly is the idea that you can use the same data types on the front end and the back end. So neither Aniket nor I have worked on this for production applications, but another one of our coworkers has put together an application that is using Rust on the back end for doing some distributed computation work, and on the front end is using Rust and WebAssembly sharing data types. So I'm guessing a lot of people in the audience are coming from the Haskell background. A lot of, we've worked in the past with GHC.js and the concept that you can use the same source files on both the front end and the back end. If you happen to be working with Rust on the front end, there can be something just very natural about using Rust and WebAssembly on the front end. The tooling is nice, and it's one of the nicest languages you can compile to on the front end. Just in case anyone's wondering, usually at FP Complete, we've been using PureScript and Halogen for I think the past 2 to 3 years now for most of our front-end work. But always interested to try out new things over here. Another question, which I think I may have just implied the answer to, what kind of intensive work were you doing that motivated your adoption of WASM for increased performance? So mostly this was actually for convenience that we were using Rust in this case. The production cases that we've had so far, plus a little bit of investigation into the possibilities. We don't have a specific high-intensity application that we've been working with so far, though those do exist in the world. Okay, and the last question was, what kind of file sizes are you seeing on WASM? How do the bytes transferred over network, overall load time on a page implemented with WASM compare today to pages written in JavaScript? Do you foresee that improving in similar ways as projects like Webpack are improving load sizes?
Well, I'm not aware of any compression that takes place when WASM files are being served, other than the usual. But that's about it. In the sense that Unity guys say that it is faster and smaller, whereas the application that we have in tic-tac-toe I guess the JavaScript payload would be much smaller than the boasting payload, which is around 600 kilobytes. Obviously, because the standard web library itself has its own event loop running inside the WebAssembly machine, and all sorts of other things. So it depends.
Another question coming in: what does your workflow look like? Do you use things like WAVM, the WebAssembly? I'm just guessing that's how people pronounce it. So WAVM is the WebAssembly virtual machine. I can.
The WebAssembly virtual machine.
Yeah, I can speak to this one if you'd like, Aniket. Personally, I haven't used. I'm not sure if people could say WAVM or not. Doesn't matter. I personally haven't needed to use it. My workflow when I've been playing around with WebAssembly has been fully to use it from inside the browser. Sometimes, if I'm working on a complex library, one of the examples that I did was actually a solver for a board game. So there was some relatively complex logic. It wasn't simply playing around with a GUI. I was able to just use standard Rust native code for doing that kind of development. I did test-driven development in that case. And then once it was done, I was able to plug it in with WebAssembly pretty easily. So that was the workflow that I've used. I'm not aware of people using something like WebAssembly VM, but for all I know, that is going on in the world. But I'm not quite sure of that one yet. Another question that came in, is Rust a must for compiling to WebAssembly? What is the status with other languages such as Haskell?
Okay, so I'm not aware of the Haskell ecosystem with WebAssembly as of now. But I know that there are JavaScript targets to Haskell. The two or three languages, I would say, that target WebAssembly very well today are C, C++, and Rust. C and C++ use the EM scripting tooling, and Rust has its own.
And there is a project in Haskell. In fact, I think there may be two different projects in Haskell to have Haskell compile via GHC compile to WebAssembly. I can't say that I'm an expert on either one of those projects, but they are both active as far as I know. I think the last I heard was that the garbage collector still needs to be implemented for at least one of them. Anyway, the projects are ongoing, and it does look like a lot of different languages out there are planning at some point to compile to WebAssembly. I also happen to know that one of the limitations with garbage collected languages is you now have to ship an additional garbage collector in addition to the fact that the web browser itself is running a garbage collected language, and there is some discussion in the WebAssembly team itself of adding garbage collection support directly into WebAssembly. My understanding is that it would be an optional add-on in the sense that you could still use Rust, C, C++, these manual memory languages without incurring any kind of a garbage collection overhead. But instead of shipping an entire garbage collector in your WebAssembly code, you would be able to use the browser's garbage collector. Okay. And last question that's on the screen now. Are you aware of Asterius? I think that's the way to pronounce it.
Oh, is it a game engine? I think so. Asterius. I'm just searching the web now. It's a GSC WebAssembly backend, and it reads sudo status. It's by the Tweak guys.
I didn't realize that was the name of it. I thought WebGHC must be the other one then.
Yeah. This seems quite good.
So yes, that if people are interested in looking into the state of these things, now we have the two different names, so Asterius and WebGHC, unless someone in the chat wants to correct me and say that's not the name of the other one. Okay. Very good.
There is a project on GitHub that's just called Haskell Ecosystem. I'm not sure. They're 360 stars and then 4 contributors. Stephen Deal is one of them.
Oh, okay. I think that's it for the questions. So Aniket, thank you very much for the presentation. Very good presentation, much appreciated. Audience, thank you very much for the great questions, the great interaction. We'll be uploading the video for this hopefully in the next few days. And we will update everyone on Twitter and elsewhere when we have our next webinar topic chosen. Thank you very much, everyone. Have a good rest of the day.
Thanks, everyone. Thanks, Michael.